Good evening, everyone. So today, I will be presenting our group's ALU design. So as you can see for the left part, there's an upper part and a lower part, but both of them are 4-bit 4-1 multiplexer. For the upper part, it is functions for the A input, and for the lower part, it is used for the B input. So let us look inside the 4-bit 4-1 multiplexer. So as you can see, it is actually a complex design inside it. It consists of 4 1-bit 4-1 multiplexer, and let's look inside 1-bit 4-1 multiplexer to look at its gate level schematic. So it's actually like this. As you can see, there are 4 AND gates, 2 NOT gates, 1 OR gate, and the output. However, these only produce 1 bit. So in order to produce a 4-bit 4 multiplexer, we have to simplify the first one and then combine all 4 of them in order to produce 4-bit data. And after that, we simplify it again to produce a block diagram like this. So like this, we can simplify the input and also the output. However, it is a 4-bit 4-1 multiplexer, which takes a 4-bit input and also produces a 4-bit output. Now, for the middle part, it's an ALU operator. So it is basically a full adder. However, when the selector is equal to 0, it will become a subtractor, and when the selector is equal to 1, it will become an adder. So now let's look into it. Now let's move on to the ALU operator. So this is the gate schematic of the ALU operator. Here there's an important note is that we have to look at the value of the selector. If the selector value is equal to 0, this ALU operator will automatically become a subtractor, and if it is equal to 1, it will become an adder. So the ALU operator is basically an integration of 4 full adder. Here the value of the selector is actually the C original input. So basically, when C equals to 0, we have to insert it as the first input. So here we can see that there are 4 SOR gates. This is because that when the selector value is equal to 0, it has to become a subtractor, right? So by using a SOR gate, we can invert all of the B input value so that it will become automatically a subtractor. We can minus the B value. So at the end, if selector value is equal to 0, it will automatically become a subtractor, and if the selector value equals to 1, the C input automatically become 1 as well, and then this part will automatically become a full adder. So that's all for the ALU operator. Now let's move on. So now for the last part, which is the register, the 4-bit register. So as we know that a 4-bit register is basically a group of flip-flop integrated together. So in this case, we use 4 positive edge trigger D flip-flop. So now that it can insert 4-bit data, and then it will produce an output of 4-bit. So basically it's it will become a shift right register. So the data will be inserted once every cycle, and then the positive edge will be sent once, and then every data will be shift right once. So at the end, we'll obtain a 4-bit output. So this is how we design our ALU. So now let's move on to the simulation result. Now let's move on to the simulation part. So here there are some important things that we have to note. First is the clock. See, it is a positive edge trigger. So for the first positive edge, the result will produce here. And also everything will start to activate here. Then the operator selector is equal to 1. So that means that it will be an adder. The reset value equals to 1 and not 0, so that means that there will be output here. Here, the selector of the A input and B input will choose 0, 0. So that means that we choose the A0 and also B0. So let's start the simulation. So here the result is produced. So as I said just now, we choose the first A0 and also B0, and it is an adder, so 1 0 0 0 plus with 0 0 0 1, it will produce 1 0 0 0, which is correct at the output. Then let us look at the second one as well. The positive edge is here. As you can see, it's also the same. The first input of A and B, 0 1 0 1 plus with 0 0 0 1, it will produce 0 1 1 0, which is also correct. So based on the two first results here, we can make a conclusion that our gate schematic is correct since the simulation result is also correct. So in conclusion, our assignment is a success. So that's all from our group. Thank you.